So this worked example is a redox titration using copper as the transition element, and we're starting off with hydrated copper sulphate. Here it is here, and as you can see we've got an X in there, and the whole question is really about finding X. How many molecules of water are in the crystalline structure of hydrated copper sulphate? Okay, so let's just read through the question so we understand what the practical is actually doing in practice. So we've got iodine thiosulphate version of redox titrations again, which we've done in class, and we're going to find X as it says. So first of all, we take some of the hydrated copper sulphate and we get its mass. Okay, and you take your two readings and you're going to work out your mass there. Then you're going to take that and you're going to put it into, you're going to dissolve it. Let's say we put it into a conical flask. So here's our conical flask, and let's say we put our dissolved, well, we put a bit of our copper sulphate in. Alright, and then we're going to react it with our iodide. Yeah, we're going to let it react, and that's going to make it's going to make copper iodide and iodine. Okay, so why do we do that? Well, we can do nice titrations with iodine, and we get a nice sudden colour change. But the reason why we're doing that is in the end, is to find out our moles of copper ions. And so then, once we've got this mixture of copper iodide and iodine, we're going to do our titration, and in our burette we're going to put our thiosulphate. So that's what's going to go in the thiosulphate. We're going to add the thiosulphate to our iodine. The iodine is going to disappear. And then we'll be able to see when it's totally disappeared. We will know what the endpoint is and be able to work backwards. Okay, so let's just make a little plan in our heads as to what we're going to do. From our titration, right, we're going to get a mean tetra from our titration, right? So our titration readings are at the bottom here, and we'll get a mean tetra from that, in which case we know the concentration. The concentration is here. All right, so we'll be able to find out the moles. We'll be able to find out the moles of thiosulphate, in which case we'll be able to find out the moles of iodine that was in our conical flask. Then that we'll take back into this equation and use the moles of iodine that were in our conical flask to get back to the moles of copper that were in the original solid sample. Okay, so then when we've got moles of copper, right, so we're going to have moles of copper ions, that's going to be immediately related to moles of this. All right, so we're going to have, because there's a 1-to-1 ratio between copper and hydrated copper sulphate, so we're going to know the moles of copper sulphate. We're going to know the mass because we've taken the mass of it before we even started, and we're going to use those two. We're going to use those two to get an MR for hydrated copper sulphate. And once we've got the MR, then the only unknown in that equation is going to be X, right? So that's going to get us X in the end. Okay, so that's the plan of what we're going to do, working all the way backwards to X from moles of thiosulphate. Okay, so let's just draw a box. I might need all this space, so I'm going to start up here. So our moles of thiosulphate. It's concentration times volume, of course. All right, and concentration we're given in the question is 0.12, and our volume. Oh yeah, we have to work out this. So separately, I worked out this tetra this mean tetra, and it's 21.75 cm cubed. Okay, so that's 21.75 converted into dm cubed. So our moles of thiosulphate comes out to be 2.61 times 10 to the minus 3, and that's per titration. Per titration. Alright, so now what we can do is find out the moles of iodine. So let's go back to our titration reaction, and you can see that, let me just change colour a sec. Alright, so you can see we've got a 2 to 1 ratio of thiosulphate to iodine. So the moles of iodine, in the titration that reacted with the thiosulphate is going to be half times the moles of our thiosulphate, and that comes out to be 1.305 times 10 to the minus 3. Okay, so now we've got the moles of iodine per titration, and from that we're going to get moles of copper. Moles of copper 2 plus ions, and we have, for that we have to come back to our first reaction. Okay, so and now we've got the 1 to 2 ratio and the other way around. Right, so there's our 2, there's our 1. So now 2 is our target molar ratio, and 1 is our known molar ratio. So the moles of copper is 2/1 times the moles of our iodine, which is 1.305 times 10 to the minus 3. Right, so that comes back to our original 2.61 times 10 to the minus 3. Okay, so that's the moles of copper ions in a titration, but of course we took a 25 cm cubed aliquot out of a 250 cm cubed volumetric flask. All right, so the moles of copper ions in the sample, moles of copper ions in the sample is 250 over 25, which is where our 10 comes from, times the moles that were in each titration, and so that is 2.61 times 10 to the minus 2. Right, and that was the amount of moles that was in our actual sample. And because we have a 1-to-1 ratio, right, so there's 1 copper ion per formula unit of hydrated copper sulfate, that also tells us that we've got the same number of moles of hydrated copper sulfate. So moles of that is the same, 2.61 times 10 to the minus 2. And that has a mass of, let's work this mass out. Mass is 5.60 grams. Okay, so therefore the MR of our hydrated copper sulfate is mass over moles. The mass was 5.6. Moles is 2.61 times 10 to the minus 2. All right, and that comes out at 214.6. Okay, so now we've got the MR of it. We can work out what X is. So we just rearrange with a bit of algebra the equation, and it comes out as 214.6. Take 159.6, which is the MR of just the copper sulfate bit, divided by 18, which is the MR of water, and that gives us the number of units of water per formula unit. The exact number is 3.05, and that rounds to 3, has to be a whole integer, and so x is 3. There, I hope that helps.